Module 5G, I want to continue practicing some of the concepts we've been covering in this chapter. So solving stoichiometric problems involving limiting reactants, reactants and precipitation reactions, and just stoich in general, and also looking at some acid-base neutralization reactions, specifically titration. So we're kind of expanding on everything we've learned in chapter 4, which was looking at stoichiometry, limiting reactant, excess reactant, if needed, if we had to. And we're going to continue that on, but looking at solutions chemistry as well. The big thing with solutions chemistry is that sometimes we have to be able to predict what the product should be. And that's where our solubility rules come into play. We have to know our solubility rules so we can say, yes, this will precipitate, and no, nothing's going to happen, so there's no reaction. First example, write the equation for the precipitation reaction between an aqueous solution of potassium carbonate and an aqueous solution of nickel 2 chloride. Now, the nice thing about this question is it's telling me right here that I have some kind of precipitation reaction happening. So I know the reaction is going to go forward. I know a solid will form. It tells me aqueous solutions of potassium carbonate and nickel 2 chloride. So I know what my reactants are, and I don't have to think much about my solubility rules. I know what they are. I will have to think about it in the sense of my products, but I know that some product is going to form. So that kind of makes this question actually makes it a little bit easier to do. Let's think about potassium carbonate. I know potassium is K, and so if it's an ionic compound, it would be potassium ion, which would be K+. I know my polyatomics. I know carbonate is CO3 2-. So I know potassium carbonate must be K2CO3. I have to have 2 potassium ions for every 1 carbonate ion because the compound itself has to be neutrally charged. I also have nickel 2 chloride. The nickel 2 is telling me the charge on that nickel. That's telling me I have nickel 2+. And chloride, I know chloride is for the chlorine ion. Chlorine is Cl. It's a halogen, and halogens always want to be a -1 charge. So I know I have nickel Cl2. I need 2 chloride ions to pair up with that nickel to make it electrically neutral. So I've got the formulas of both my reactants now. I'm going to determine the possible products, and that's where we crisscross. You take the cation from one half and put it to the anion of the other. Cation from one half to the anion of the other. So where cation replaces cation, anion replaces anion. And I want you to think about that a little bit further as well. That means cation or metal replaces cation, and anion or nonmetal replaces anion. Well, the reason I'm saying that is when we get into single displacement reactions where only one species being displaced, metals want to be cations. So if anything's going to happen, it's going to be that metal swapping out. Don't pair up a metal, which will behave as a cation, with another cation. Don't pair up a nonmetal, which will behave as an anion in solution, with another anion. Cations and cations don't like each other. Anions don't like each other. Cations want to be with anions. So even in a single replacement reaction, which is not this case, I know this is double replacement, both things are swapping, but in single replacement, you need to think about what those things will form in solution. You can also think about what this actually means in solution. If I have K2CO3, I've got a beaker, and I've got 2 potassium ions for every 1 carbonate ion. If I've got nickel 2 chloride, I have a beaker where I have 1 nickel 2+ ion for every 2 chloride ions present. And I am mixing these together. When I mix these all together, I've got K+, CO3 2-, that should be a 2 in there, I apologize, there should be a 2- right there. Nickel 2+, and Cl- and Cl-. So this is what's actually happening in solution. This is what we call your particulate diagram. And sometimes you'll see these circled because they are little ions floating around in solution. And again, the ions themselves are surrounded by water molecules. That's what stabilizes them in solution and allows them to exist as individual ions. But this is my reactants. I'm determining the possible products by crisscrossing, but I can also look at the particulate diagram and see that as well. So possible products here would be K2Cl or sorry, no, not K2, I apologize, I'm reading the wrong thing there. Remember that's K plus and Cl minus. It's almost easier to see with the particulate diagram. The K and the Cl will pair up. The K plus and Cl minus are each plus one charge minus one charge, so KCl. And then the other species that could pair up here is my nickel 2 plus and my carbonate CO3 2 minus, which would give me NiCO3. So I'll write the formulas of the products. Well, that's what I just did. Determine if the products are soluble or not. Now, you got to remember your solubility rules to do this. K plus is a, potassium is an alkali metal, group 1. Group 1 salts are always soluble, no exceptions. Chloride ion, usually soluble. The chloride salts are usually soluble unless they're paired up with some very specific elements. You need to know your solubility rules there. Think about what it means. When is chloride not actually soluble? And if you remember back to your solubility rules, you will know that chloride ion is always soluble unless it's paired up with copper plus 1, silver ion, which is just silver plus 1 because silver can only be a plus 1 charge, the mercury 1 ion, which is that Hg2 2 plus polyatomic, and lead 2 plus. I didn't mean to erase that so fast, I apologize. The Hg, having a hard time writing that. Hg2 2 plus, copper plus, silver plus, lead 2 plus. That's when chloride would not be soluble. This does not fit any of those cases, so this is going to go ahead and be KCl will be soluble. The other product we have is nickel carbonate, nickel 2 carbonate specifically. Carbonates are not actually usually soluble. Most carbonates are insoluble, and this is not an exception to that. Exceptions would be like if they're with a group 1 salt, if you have them with ammonium, but this is insoluble. Which means what's actually happening in solution is once they find each other, these two are pairing up and forming a solid. So in the beaker over here, this is actually what's being shown. You've got K plus ions floating around. Let's write those in a color that shows up better. We've got K plus ions floating around, Cl minus ions floating around, but this solid in here is nickel carbonate. And then write the phase notation and balance the overall reaction. K2CO3, I know is aqueous. NiCl2, I know is aqueous. Forming KCl, I know is aqueous. And NiCl3, which I know is solid. Need to balance this. I have 2 potassium on the reactant side, so I need 2 potassium on my product side. 1 carbonate on each side, 1 nickel on each side, and now I have 2 chloride on each side, and the reaction is balanced. Let's look at our next example. Lead 2 nitrate. So let's think about what that means. Lead 2 nitrate, Pb2 plus, nitrate is Ni3 2 minus. So I've got Pb NO3 reacts with cesium sulfate, cesium, Cs plus, sulfate, SO4 2 minus. So I've got CS2, SO4, in an aqueous precipitation reaction. What are the formulas of lead nitrate and cesium sulfate? Well, conveniently, we just answered that. Write the molecular equation and anion equation for the reaction. My molecular equation is the complete neutral species in solution. So PbNO3, 2 is aqueous, nitrate is always soluble. Cesium sulfate is soluble. Cesium is a group 1 alkali metal, so its salts are always soluble. We're going to swap partners here. So the lead is going to go to the sulfate. Cesium is going to go to the nitrate. PbSO4, CsNO3. Because again, Cs is a +1 charge, NO3 is a -1 charge, one of each to pair it up. Lead 2 plus is a +2, sulfate's a -2, so 1 to 1 to pair it up. Now I gotta remember my solubility rules. I know the first one I'm going to do is cesium nitrate, because that's the easiest for me. I know nitrates are always soluble, and I know cesium is an alkaline metal, or group 1 metal, and they are always soluble. So that will be aqueous. I know sulfates are often soluble, but I know with lead 2 plus they are insoluble, so that will be a solid. I know the question doesn't ask for it, but if I had drawn the particulate diagram, what I would have here, in beaker 1, Pb2 plus for every 2 nitrates. In beaker 2, 2 CS pluses for every 1 SO4 2 minus. And in my product, I would still have those NO3 minuses floating around, the CS pluses floating around, but my Pb and my sulfate would be pairing up, forming a solid. So I wrote the molecular equation, write the net ionic equation for this reaction. The easiest thing to do when you're doing net ionic is to look at what is the driving force of the reaction. The driving force is the formation of that insoluble product, whether it be gas phase, liquid phase, or a solid phase, just not aqueous phase. That's the driving force. So whatever goes into making that is what's important for that net ionic. So if I'm going to make PbSO4, what came from the other pieces to make that? That was made by Pb2 plus and SO4 2 minus. Notice in my reaction above, we initially had all these ions floating around. We mixed them together, the cesium ions are still floating around, the nitrate ions are still floating around, but the lead ion, when it finds that sulfate ion, they form that solid, and they are no longer floating around. They are now forming a solid. And so it's the presence of those two things that make this reaction go forward. So we've got, let's see, formulas of lead nitrate and cesium sulfate. We've got molecular equation, we've got net ionic equation, we've got the names of the products. What are the names of our products here? This is lead. 2, we have to specify the charge here. Sulfate. And cesium nitrate. The last thing I could ask, it's not asked in this question, but what if I asked you what the spectator ions were? The spectator ions are the ions that aren't going to do anything in the reaction itself. If I look at this reaction, the lead and the sulfate paired up to make lead sulfate. That's doing something. But the nitrate stayed floating around as nitrate. Cesium ion stayed floating around as cesium ion. So my spectator ions are my nitrate ions and my cesium ions. Let's work another example. What volume of 0.1 molar MgCl2, magnesium chloride, is required, let's write that so you can read it, is required to precipitate all of the silver from 10 mils of a 0.1 molar silver nitrate solution. So just like we've done all semester, I need you to think about the balanced equation here. Well, first, I want you to write down what you're trying to find. That's what we've done all semester. Number of mils of MgCl2. When I say volume, I need mils. I'm not going to measure out liters because we just aren't going to work at that scale. But in order to do this, I'm going to need the balanced equation. I don't know how many magnesium chlorides react with how many silver nitrates. So let's go ahead and get our balanced equation. Magnesium chloride, I know is soluble. Chloride salts are usually soluble. Magnesium chloride is not an exception. Reacts with silver nitrate. Nitrate salts are always soluble, with no exceptions. And I'm going to swap partners. cation to anion, cation to anion. It's going to give me magnesium nitrate. Notice that magnesium is a +2 charge. How do I know that? Well, two things. One, I know that magnesium is always +2. It's group 2. It's an alkaline earth metal. But two, I see it's paired up with magnesium chloride. So what that really means in solution is I have magnesium 2+ for every 2 chloride ions. I know silver nitrate. Silver is always +1, nitrate is -1. So I need 2 nitrates for every 1 magnesium. I also know that's soluble because because nitrate salts are always soluble. And silver chloride, which is solid. It does form precipitate. Chlorides are usually soluble, but silver is one of the exceptions that will precipitate out. So what we're really doing here is we're thinking about if we mix these two together, what's going to form. And I see that my chloride ions will pair up with my silver ions in a 1-to-1 ratio. What that does is leaves behind my magnesium and my nitrate ions, and in the molecular equation I write them together, but really my magnesium and nitrate are my spectators. So I know what product I'm forming. I need to look at my equation. It's not balanced yet. I definitely need to balance it. And I know I keep drawing these particulate diagrams and going off sideways, but it's because I want you guys to see what it is. We need you to be able to see what's in solution. I've got 1 magnesium on each side. I have 2 chloride on my reactant side, so I need 2 chloride on my product side. I now have 2 silver on my product side, I need 2 silver on my reactant side, and now I have 2 nitrates on each side. My reaction has been balanced. So back to the original question, how many moles of magnesium chloride do I need? I'm starting off with a 0.5 molar solution, which means 0.500 moles of silver nitrate per 1 liter of solution. And I'm starting with 10 mils of that solution. 10 mils is the same as 0.010, keep your sig figs, 0 liters of silver nitrate solution. At this step right here, I've canceled out my liters of silver nitrate and I have moles of silver nitrate. Now I can use my balanced equation to calculate 2 moles of magnesium chloride because that's what I'm trying to solve for. I'm trying to find mils and I need to go through moles to get there. I see that it's 1 mole magnesium chloride reacting with 2 moles of silver nitrate. That cancels out my moles of silver nitrate and I have moles of magnesium chloride. Now this is where some students are going to get stuck. They're going to say, okay, but that doesn't help. I don't know how to get out of moles of magnesium chloride. I need, milliliters here. Don't forget that your molarity is a conversion factor. By saying 0.100 molar MgCl2, I can say 0.1 moles magnesium chloride to 1 liter of solution, specifically magnesium chloride. Or I can flip that the other direction because it's an inequality, it means it equals 1. I'm going to write 1 liter magnesium chloride solution for every 0.1 moles of magnesium chloride. Now that will get me liters. I do want milliliters just because we're not going to work in liters. You don't have to show this step. You can just do this step in your head for all I care. You do need to show all of this. So all of this would need to be shown. Okay? This last step converting to mils, you can do it in your head, I don't care. But this will give you 25.0. I have 3 sig figs. 3 here, 3 here, 3 here. So 3 sig figs, 25.0 mils of 0.100 molar MgCl2 will be required to precipitate out all of my silver nitrate as silver chloride. What about this example? What massive calcium carbonate is formed when 25 mils of 0.12 molar calcium nitrate solution is mixed with 30 mils of 0.110 molar potassium carbonate solution? Write out your balanced equation first. Calcium nitrate, CaNO3, 2. I know calcium is group 2, alkaline earth metal, so it's +2 plus charge. Nitrate is a -1 charge. That's so you can read it. So it's going to have 2 nitrates for every 1 calcium. Nitrates, always soluble, no exceptions. Potassium carbonate, potassium, K+, carbonate, CO3, 2-. So I'm going to have 2 potassiums for every 1 carbonate. Also soluble. Carbonates are not always soluble, but potassium is always soluble. Potassium salts, that's a group 1 salt. Alkali metal, potassium is an alkali metal, their salts are always soluble. Swap your partners. Calcium to carbonate, potassium to nitrate. So CaCO3, again calcium +2 charge, carbonate -2 charge, and KNO3. Potassium is a +1 charge, nitrate is a -1 charge. Both potassium and nitrate are always soluble, no exceptions, so that will be aqueous. Carbonates are not usually soluble, there are exceptions to that, but calcium carbonate is not an exception, that will be insoluble. Now we've got your balanced equation, or now you've got your equation, we need to balance it. I see that I've got 1 calcium on either side. I've got 2 nitrates on my reactant side, so I need 2 nitrates on my product side. Let's see if I can erase this just to get the space cleaned up. And 2 potassiums on each side, 1 calcium, 1 carbonate on each side. Perfect. Reaction is balanced. But what I want you to recognize now, what I like to do, you can do whatever you want. What I like to do is I like to write under the reactant itself what I have of it. And it tells me for calcium nitrate, I have 0.120 molar and 25 mils. For potassium carbonate, I have 0.110 molar and 30 mils. Because I'm given volume and concentration for each species, that means that this is a limiting reactant example. So I'm going to solve it a couple different ways just to show you guys what you can do. Again, you can do it any way you want. As long as you're getting the right answer in the end, there are multiple ways you can do this. I'm going to do it one way where I just calculate the product of both and compare. Then I'm going to erase it and do the 6-step method. Okay? So, first one. If calcium nitrate is my limiting reactant, how much product can I make? I want to know calcium carbonate formed. That's the product I'm interested in, so that's what I'm going to calculate too. I have 0.120 moles calcium nitrate per 1 liter of solution of calcium nitrate. I have 25 mils of that solution, 0.0250 liters of calcium nitrate. Now I'm trying to get to how many grams I'm going to make here. Mass means grams. I see that it's 1 mole calcium carbonate being formed for every 1 mole calcium nitrate consumed. Mathematically, this step does not matter, but you have to write it down if you want full credit because it's showing the proper conversions. Now convert to grams of calcium carbonate, add the molar mass of calcium carbonate, and you find that the molar mass is about 100.1 grams per mole. And we get an answer here of 0.300 grams calcium carbonate. So that means one option, 0.300 grams. But that doesn't mean it's for sure the answer. I have to see how much I can make with the. What if K2CO3 is my limiting reactant? I'm going to follow the same process. 0.110 moles of K2CO3 to 1 liter of solution, specifically to the K2CO3 solution. We have 30 mils, which is 0.0300 liters. Still a 1-to-1 ratio. 1 mole K2CO3 to 1 mole of, not K2CO3, sorry, 1 mole of calcium carbonate to 1 mole of K2CO3 and 100.1 grams calcium carbonate to 1 mole of calcium carbonate. If you're ever unsure if you're doing it right, remember your units should always cancel. So checking back, liters of solution, calcium nitrate, liters of solution, calcium nitrate, moles of calcium nitrate, moles of calcium nitrate, moles of calcium carbonate, moles of calcium carbonate. I got to grams calcium carbonate. Liters of potassium carbonate, liters of potassium carbonate, moles of potassium carbonate, moles of potassium carbonate, moles of calcium carbonate, moles of calcium carbonate. I'm to grams of calcium carbonate. I calculate this out and I get 0.330 grams CaCO3. So 0.330 grams. Now I compare the two numbers and I say which one's bigger, or which one's smaller. Sorry, I apologize, which one's smaller. 0.0300 grams is a smaller value. That's the most I can make. That also tells me that calcium nitrate was my limiting reactant. It's going to make the smallest amount of it. So calcium nitrate is my limiting reactant. We can form 0.300 grams of calcium carbonate under these conditions. I know some students really like doing the 6-step method though, so let's go ahead and do the 6-step method as well and show the same results. Let's not erase our whole balanced equation though. Sorry, I should think about what I'm erasing here. There. 6-step method has us first convert all of our reactants to moles. So number of moles, CONO3, 2, is equal to 0.120 moles, CaNO3, 2, to 1 mole, 1 liter, CaNO3, 2. I have 25 mils, 0.0250 liters of CaNO3 solution. And I don't actually have this written out, so let's go ahead and calculate it. 0.12 times 0.025, 0.003. That's what my calculator gives me. You need to keep your sig figs. Put 2 more zeros there. 0 moles of CaNO3. 2. Do the same thing, number of moles of my other reactant, K2CO3. I have 0.110 moles, K2CO3, to 1 liter of K2CO3. I have 30 mils, which is 0.0300 liters, K2CO3. 0.11 times 0.03, 0.00300 moles, K2CO3. Now I'm going to compare the two and see which one my limiting reactant is. Students always get creeped out by the way I pick them. It doesn't matter. I just pick the first one. I always just say, if my first reactant that I've written down in the reaction is my limiting reactant, how much of the other one do I need? Or, I'm trying to think of how I do this. I always pick the first one. Let's do it. How many moles calcium nitrate are needed to react all of my K2CO3? Again, it doesn't matter which way you do it, but I need I apologize, this should definitely be a different number in here. This should definitely be 0.00330. Please fix that in your notes. If I want to react all of my K2CO3, I have 0.00330 moles K2CO3, 1 mole of calcium nitrate reacts with 1 mole K2CO3. So I would need 0.00330 moles calcium nitrate to react all of this. And I ask myself, do I have enough? I say I need this much, I have this much. Do I have enough? The answer is no, I don't have enough, which means this is my limiting reactant, this is my excess reactant. Now I go back in and I shrink all of this so we can fit it on the slide. And I say now with my limiting reactant, number of grams I can make of calcium carbonate based on that limiting reactant. 0.00300 moles calcium nitrate. I know that 1 mole of calcium carbonate is produced for every 1 mole calcium nitrate consumed. And I know the molar mass of calcium carbonate, because I added that up, is about 100 grams, 100.1 grams calcium carbonate to every 1 mole of calcium carbonate. And I will make 0.300 grams calcium carbonate. So again, you can do it with the 6-step method as well. It works just as well. I just did it the other way because it's, for me, a little bit faster. But I want you guys to do the way that makes the most sense to your brain, okay? Find the method that works for you and go with it. Let's look at some net ionic equations. Write the net ionic equations for the following reactions. I have nitric acid, reacting with calcium hydroxide, so I've got a strong acid reacting with a strong base. When you have a strong acid and strong base react, the result is always salt plus water. Cation from one, in this case the H plus the cation, anion from the other, which is hydroxide. Cation from one, anion to the other. So salt would be calcium nitrate. Potassium is an alkaline earth metal. When in ion form, it is calcium 2 plus. We need 2 nitrates to charge balance it. Nitrates are always soluble. And water. We do have to balance this, so we will have to have 2 waters. This is the molecular equation. Let's look at our net ionic. The net ionic looks at the driving force of the reaction. So basically, you're looking at how did we form this? How do I form 2 moles of water? Well, my 2 protons from my acid reacted with my 2 hydroxides from my base to form water. But remember, balanced equations need to be in the simplest form. So I'm saying H plus OH minus gives me water. So the actual net ionic equation here is H plus OH minus giving me water. Now the next one shown here is acetic acid. You do need to know acetic acid. It's the 1 weak acid. You need to know the formula of it. It looks a little weird. Most of you guys have learned acetate as C2H3O2 minus. If you put an H with that, C2H3O2H. I don't care how you guys write it. I'm going to write it like this. You have to be able to recognize I'm writing it like this. You can write it however you want as long as you get the right formula, but you have to recognize this is acetic acid. And potassium hydroxide. So acetic acid is a weak acid. Potassium hydroxide is a strong base. Weak acids do not dissociate 100% in solution. We'll delve a lot more into this in Chem 2, But for right now, you need to understand the way they're reacting. It's still an acid and base reaction. They still form salt plus water. But even though it's aqueous here, that doesn't mean I split it apart. I'm still going to keep it intact. It's going to form salt plus water. Now the salt it forms is going to be KCH3COO from K plus and CH3COO minus. Both K plus and CH3COO minus are always soluble, so CH3COO minus will be in solution, plus water. And on this side we have hydroxide. What happened to my potassium? Why didn't I put the potassium in here? My K is a spectator ion. And methylamine is a weak base. We're going to get more into bases in second semester. But if I tell you something is a base, you have to recognize that it steals the proton. A base also forms hydroxide in solution. So to form hydroxide in solution, that proton had to go somewhere, and it goes to the methylamine, giving it a positive charge. So there's not a real spectator in that reaction. In this first reaction, the spectators are your calcium and your nitrate. In the second one, your spectator is potassium ion, and this one doesn't have a spectator. The titration of 10 ml of HCl of an unknown concentration requires 12.54 ml of a 0.1 molar sodium hydroxide solution to reach the endpoint. What is the concentration of the unknown HCl solution? So you're doing a titration. You've got your Erlenmeyer flask. You've got some HCl in here, specifically 10 mils of it. We've got a burette up here, and we've got sodium hydroxide in here. And so we're slowly adding in sodium hydroxide. If you want to look at the net ionic here, OH minus plus H plus gives you H2O liquid. Here's the trick. The net ionic of a strong acid plus a strong base is always H plus OH minus, giving you H2O liquid. No exceptions to that. It's kind of a little shorthand. But my reaction is balanced. And so I'm basically just neutralizing the hydrochloric acid in there. I'm told that I have 10 mils of HCl. I have a 0.1 molar solution of NaOH and 12.54 mils of it. I want to know the molarity of HCl. Concentration, though, it says concentration, that means molarity unless otherwise specified. That's the same as the number of moles of HCl to liters of HCl solution. I'm going to start with sodium hydroxide because that's all I know. I have 0.100 moles of NaOH to 1 liter of solution, and it took 0.01254 liters of the NaOH solution to reach the endpoint. The endpoint is when the number of moles of HCl are chemically equivalent to the number of moles of NaOH. What I mean by chemically equivalent is this reaction is a 1-to-1 ratio, 1 mole of HCl to 1 mole of sodium hydroxide, so 1 to 1. If I had used a different base source, like say calcium hydroxide, it would be half as many calcium hydroxide ions for 1 mole of HCl. Chemically equivalent by moles. This cancels out my liters of solution. And again, this is sodium hydroxide solution down here. I have moles of an AOH. My balanced equation tells me that 1 mole of HCl reacts with 1 mole of sodium hydroxide. I've got my moles of HCl, so I've got my numerator. How do I get my denominator? I just want that per moles of solution. So I'm going to say 1 over 0.01, stick figure 0.123 liters of HCl solution, because that's how much solution was used. I've got my numerator, I've got my denominator. This equals out to 0.125 molar HCl. So if 10 mils of HCl took 12.54 mils of a 0.10 molar solution of sodium hydroxide to reach the end point, I know the concentration of HCl is 0.125 molar. Okay. A 15 ml solution of barium hydroxide is neutralized with 30.5 mils of 0.2 molar hydrochloric acid. What is the concentration of the original barium hydroxide solution? Barium hydroxide, BaOH2, strong base, so soluble. Reactions hydrochloric acid, HCl. Swap partners, I'm going to form barium chloride, 2 chlorides for every 1 barium, and water. Definitely need to balance my reaction here. 2 in front of the water, 2 in front of the HCl. I'm trying to find the molarity of my barium hydroxide, but I'm told I have 15 mils of it, which is the same as 0.0150 liters of solution. In my HCl, I have 0.2 molar and 30.5 mils, which is the same as 0.0305 liters. So I want the molarity of barium hydroxide, which is the number of moles of barium hydroxide, 2 liters of barium hydroxide solution, I'm going to start with my HCl, because that's what I know. I have 0.200 molar, which is 0.200 moles of HCl for every 1 liter of HCl solution. I have 30.5 mils, or 0.0305 liters, so times 0.0305 liters of HCl solution. Now I'm in moles of HCl. Now I can use my balanced equation. 1 mole barium hydroxide for every 2 moles of HCl. I've got my moles of barium chloride, or barium hydroxide, which is what I want in my numerator. Now I just need to get that over liters of barium hydroxide. I know in total I had 0.0150 liters of the barium hydroxide solution. Now I've got my denominator. Calculate that through, and I get a concentration of 0.203 molar barium hydroxide. Because again, that gives me 0.203 moles of barium hydroxide per 1 liter barium hydroxide solution. And our last example in this module, sodium hydroxide reacts with nickel 2 nitrate. What is the balanced chemical reaction? Well, sodium ion, Na+, hydroxide OH minus, so I know that must form NaOH. NaOH is a strong base, so it is always soluble, aqueous phase. Reacts with nickel 2 nitrate, nickel 2, Ni2+, nitrate, NO3 minus. I need 2 nitrates for every 1 nickel, and nitrates are always soluble. Swap partners. sodium to nitrate, nickel to hydroxide. Gonna give me NaNO3, 1-to-1 ratio, and NiOH2. I need 2 hydroxides for every 1 nickel. Nickel hydroxide, it is a hydroxide, but it's not a strong base. Hydroxides are usually insoluble, and this is not an exception because it's not a strong base, so this will be insoluble. Next, I want to know what the spectator ions are. Well, to do the spectator ions, you really need to think about what's in solution and what's not doing anything. So let's think about what's in solution. In this first picture, in this second picture, and in the product side. Here I have sodium ions and hydroxide ions. They're just floating around being supported by water, minding their own business. Nickel nitrate, I have a nickel ion, 2+, 1 nickel 2+ for every 2 nitrates in solution. Product side, let's actually balance your reaction quick. So 1 sodium to 1 sodium, 1 hydroxide, 1 hydroxide. I need 2 here to balance out my nitrates, which means I need a 2 here to balance out my sodiums. That balances out my hydroxides as well. So I have 2 sodium ions just minding their own business, floating wherever they want to be. 2 moles of nitrates, same thing. Now the nickel hydroxide is forming a solid. So that is staying together, and it's actually going to crash out and fall to the bottom of your beaker. But these ions are floating around. So my spectator ions here are the things that are not pairing up. My Na+ or sodium ion, and my NO3- or my nitrate ion are my spectator ions. Now it says if 28.5 grams of sodium hydroxide reacted with 0.525 liters of a 1.25 molar solution of nickel 2 nitrate, how many grams of precipitate would form? Well, the precipitate is the nickel hydroxide. I'm given grams of one species. I'm given the volume and concentration of the other. Both of those can lead me to moles, so this is a limiting reactant problem. So first, let's figure out the number of moles of each species. I don't have much room. I don't really want to shove this. Let's see, number of moles, NaOH. 28.5 grams of NaOH, 1 mole of NaOH, to 40.00 grams for NaOH. This gives me 0.713 moles of NaOH. Okay, let's just write that up here. 0.713 moles. I know I have 1.25 molar of nickel nitrate, so number of moles, nickel 2 nitrate, if I take that and multiply it by its volume, I'm going to get the moles of nickel 2 nitrate. I have 1.25 moles nickel 2 nitrate per 1 liter of nickel 2 nitrate solution. And I have 5.25 liters of that nickel 2 nitrate solution. This is going to give me 0.656 moles of the nickel 2 nitrate. Again, I can't just compare those number of moles to each other though. Students are naturally going to tell me that nickel 2 nitrate is the limiting reactant because there's less moles of nickel 2 nitrate. But the reaction is not happening in a 1-to-1 ratio. So I need to see how many moles of NaOH do I need to react all of my nickel 2 nitrate. I know I have 0.656 moles of nickel 2 nitrate. It takes 2 moles of sodium hydroxide to react 1 mole of nickel 2 nitrate. This would give me 1.31 moles of NaOH needed. I say, do I have enough? I have 0.713 moles of NaOH. So no, I don't have enough, which means this is my limiting reactant, and this is my excess reactant. So the limiting reactant is going to limit how much product I can actually make. I'm going to use that value to answer the question. How many grams of precipitate can I form? Number of grams of nickel 2 hydroxide, 0.713 moles sodium hydroxide, 1 mole of nickel 2 hydroxide is formed for every 1 mole, or every 2 moles, every 2 moles of sodium hydroxide reacted. When you add the molar mass of nickel 2 hydroxide, you find it to be 92.71 grams, NiOH2, to every 1 mole NiOH2. This gives me 33.1 grams, 3 sig figs, of nickel 2 hydroxide. So with this example, I could make just over 33 grams, 33.1 grams of nickel 2 hydroxide under these conditions.